Hello and welcome back to another video to help you guys have confidence on the TEAS exam. This portion deals with solutions and solubility. There are so many formulas that you will have to remember and recall and apply. But guess what? Yours truly, Professor T.K. the Chemist, is going to give you all tips and tricks and strategies to help you ace that portion of the TEAS exam. Are you ready? Let's go! So you're probably wondering, what do you need to know about solution calculations? Well, one of the major parts that the TEAS exam will highlight deals with drug dosages. Molarity and molality are used in pharmacology to calculate the precise doses of medications. Accurate concentration measurements ensure that patients receive the correct amount of a drug, which is critical for effectiveness and safety. Now, there are several different units you all will have to know about, such as parts per million and parts per billion. Those units are used in toxicology to determine exposure levels to various chemicals or contaminations in the human body. Now, when we go through these calculations in part 2 of our videos, I'm going to show you exactly how to know what they're giving you, what's required, and how do you go about applying those calculations. So let's continue our conversation. These are the keywords you need to be familiar with for this section: homogeneous and heterogeneous mixtures, solubility, solutions, solvents, saturated, unsaturated, and supersaturated solutions, and of course the units of parts per million, parts per billion, parts per thousand. Also, molarity and molality calculations. The first term you need to know is homogeneous mixtures. What does that mean? Well, homogeneous mixtures is a combination of two or more substances where the components are uniformly distributed throughout the mixture. Here are some characteristic traits you need to be familiar with. Number one, the mixture appears the same throughout, so there are no visible different parts. Number two, the composition is consistent throughout the entire mixture. And number three, the components are not easily separated by physical means. So some examples that you will come across that deals with homogeneous mixtures are salt water, air, vinegar, brass, steel. Remember, they have uniformity throughout. You cannot distinguish different components of a homogeneous mixture. Next term, heterogeneous mixture. A heterogeneous mixture is defined as a combination of two or more substances where the components are not uniformly distributed throughout the mixture. So in other words, the different parts of the mixture are visible. The composition varies from one part of the mixture to another. The components can often be easily separated by physical means such as filtration, decantation, or using a magnet. So some of your examples are salad. I love salad with all kinds of vegetables on there. You can actually see the different components of the vegetables on my salad. A chocolate chip cookie, like in this picture that I have here. A chocolate chip, you can see the different chocolate chips throughout the cookie. Soil, granite, oil, and water. So remember, a heterogeneous mixture is simply a combination of two or more substances where the components are not uniformly distributed throughout the mixture. So you have a little bit of this and a little bit of that that comes together, but when you shake it, they separate, okay? So if you think about Italian dressing, when you shake up the bottom, the vinegar and the oil will separate from each other. So that's one way that you can kind of use that as an example to help you remember heterogeneous mixtures. Now, when we talk about solutions specifically, a solution can be defined as a homogeneous mixture composed of two or more substances. So in a solution, a solute is dissolved in a solvent, creating a single phase mixture. So when we talk about a solute, that's typically like your salt. A solvent is more so like your water, okay? So here's an example. Salt water is a common way to describe solutions, okay? The salt, which is the solute, is dissolved in water, which is the solvent, forming a homogeneous mixture where the salt is uniformly distributed throughout the water. So if you have a little scratchy throat, okay, you just take you a little bit of salt and add it to your water, and it will become Homogeneous. However, there are some other terms that we're going to discuss that determines whether or not this solution is saturated, supersaturated, or unsaturated. Another key term you need to be familiar with is solubility. Now, you're probably wondering, well, what is solubility? Well, solubility is the maximum amount of a solute that can dissolve in a solvent at a specific temperature and pressure to form a saturated solution. So here are some real life examples that we often can relate to. Sugar. Y'all know sugar has a high solubility in water, right? Meaning you can dissolve a large amount of sugar in water before the solution becomes saturated. However, the solubility of sugar in cold water is less than in hot water. So think about this. If you down south, here we love tea. Some folks, though, want unsweetened tea. However, for those of you all that like tea with sugar in it, if you add sugar to the tea when it's cold, the solubility is not going to be as favorable. However, if you add that same amount of sugar to, let's say, warm water, the solubility is even better, meaning it's going to dissolve a lot quicker. So you'll have some folks that will add a lot of sugar to it when the water is cold, and they're wondering, gosh, this still doesn't taste sweet. That's because the solubility has not really responded well when the water is cold. So remember, solubility means that at specific temperatures and pressures, that's when you'll have a saturated based solution. Solvents. Well, a solvent is the substance in a solution that dissolves the solute, typically present in the greatest amount. It determines the state of the solution, liquid, solid, or gas. Some real life examples, y'all know that water is the universal solvent because it can dissolve a wide variety of substances. Like I said before, if you like your tea, sweet, 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 there's your example. In a cup of coffee, water acts as a solvent that dissolves the ground, coffee grounds, and sugar and other additives. So, again, remember, the temperature and the pressure will oftentimes be the determining factor of how much that solute will dissolve in that solvent. And remember, water is the universal solvent. Here's one of the first words that relates to solutions that you need to be familiar with on the TEAS exam, and that is saturated solutions. A saturated solution contains the maximum amount of solute that can dissolve in the solvent at a given temperature and pressure. So any additional solute will not dissolve and will remain undissolved in the mixture. So again, a real life example, if you add sugar to iced tea until no more sugar dissolves and some remains on the bottom, okay, of that glass, the tea is a saturated solution. The undissolved sugar indicates that the solution has reached its solubility limit. So the next time you go to the restaurant and you see that there is still sugar on the bottom of someone's glass, just think there is some chemistry there, okay? This particular solution is a saturated solution. Unsaturated solutions. Well, an unsaturated solution contains less solute than the maximum amount that can dissolve at a given temperature and pressure. More solute can be added and will still dissolve in the solvent. Here's an example. If you dissolve a small amount of salt in water and it all dissolves with no residue, the solution is unsaturated. You can continue to add more salt until the solution becomes, that's right, saturated. Now, I know we talked about how some folks love a lot of sugar in their stuff, okay, in their tea specifically. But here is the deal. If you have what's called a supersaturated solution, that means your solution contains more dissolved solute than would normally be possible at a given temperature. This is achieved by dissolving the solute at a higher temperature and then slowly cooling the solution. So here's a real life example. I know a lot of children love rock candy. I don't particularly care for it because it's like, ooh, it's just nothing but sugar. And here's why. rock candy is made from a supersaturated sugar solution. Sugar is dissolved in boiling water to create a supersaturated solution, which then cools slowly. As it cools, the excess sugar crystallizes out of the solution, forming rock candy. And you can also add flavors to it if you want, so that you'll have some variety in your rock candy concoctions. Now, to apply some chemistry to it by looking at a curve, because you will see examples like this on your TEAS exam. You have to be able to analyze graphs and charts of this nature to see how well you're able to think and process this information. So look at this solubility curve. We actually talked about this in one of our prior units when we discussed water solutions and their properties. Here's a classic example of what you will see. The solubility curve illustrates how the solubility of a substance changes with temperature. We've discussed this several times throughout our unit today. For most solids, solubility increases with temperature because higher temperature provides more kinetic energy to break intermolecular bonds in the solute and solvent, leading to increased dissolutions, okay? So again, as you look at this here, you will notice that the solubility of KNO3, potassium nitrate, in water, it'll actually increase significantly with the temperature. So an explanation to further give you all an idea of what we're talking about, as temperature rises, water molecules move faster, vroom, 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 and they interact more effectively with potassium nitrate molecules, overcoming what's called lattice energy more easily due to what? Increased energy. So just remember, the relationship between temperature and solubility varies depending on whether the solute is a solid, liquid, or gas, and the nature of the solvent. And I want to continue to reiterate these points again as it relates to the solubility of solids in liquids. So for most solid solutes, solubility increases as the temperature of the solvent increases. Again, this is because higher temperatures provides more kinetic energy to the molecules, allowing the solvent molecules to more effectively break apart and surround the solute particles. Again, you remember the example that I gave you before, like sugar water, how sugar dissolves more readily in hot water than in cold water. So again, you must remember, as the temperature increases, more sugar can be dissolved, leading to a higher solubility at higher temperatures. And finally, as it relates to the solubility of gases in liquids, unlike solids that we just discussed, the solubility of gases in liquids typically decreases as the temperature increases. Higher temperatures give gas molecules more energy, causing them to escape from the liquid into the gas phase. So think about a nice can of your favorite drink. Mine is Dr. Pepper. Shh, don't tell nobody. Carbon dioxide is more soluble in cold water than in warm water, which is why carbonated drinks tend to go flat faster when they are warm. The gas escapes more readily at higher temperatures. And this is also dealing with what's called Henry's Law. So if you open up that can of soda and you hear all that fizz, if it's warm, guess what? Your drink is gonna go flat. That's why folks love ice in their drinks. I'm just saying. Now, let's get into some formulas that you have to be familiar with. Here's one, for instance, that deals with parts per million, ppms. The definition of parts per million is a unit of concentration that denotes the number of parts of solute per million parts of solution. So here's your formula. And again, we're going to dive deeper into this formula where we'll do calculations that shows you how to apply this formula. Okay, so if you can remember that parts per million equals the mass of the solute divided by the mass of the solution times 10 to the 6th power, this will be quite simple for you all to remember. Okay, so this formula again is used when you're calculating volume and solutions when both of them are in volume. So you can use them interchangeably. parts per million. Parts per billion with the B. Parts per billion is a concentration that denotes the number of parts of solute per billion parts of solution. So again, the formula is similar to parts per million, but in this case, it deals with, again, still mass of the solute divided by the mass of the solution, but instead of multiplying it times 10 to the 6th power, you're doing it times 10 to the 9th power because of the billion, okay? Now, you can also use this other formula here when calculating volume when both solutes and solution units are in volume. So again, it's the same type of formula throughout: parts per million, parts per billion, and parts per thousand. They are the same except for what you're multiplying them by. Now, when do you use parts per billion? Parts per billion is used when you have low-level concentrations, often in cases where the presence of a substance must be measured with extreme sensitivity, such as toxicology reports. And then there was parts per thousand. Parts per thousand, again, is a unit of concentration that denotes the number of parts of solute per thousand parts of solution. Here's your formula. Parts per thousand is equal to the mass of the solute divided by the mass of the solution times 10 to the third, okay? Again, here's another formula that you can use when both solutes and solutions are in volume. Again, it's the volume of the solute divided by the volume of the solution times 10 to the third. So again, here's a summary in terms of the differences between the concentration units of parts per million, parts per billion, and parts per thousand. Parts per million is a suitable measurement concentrations that are relatively higher and more detectable in common environments. So you normally see parts per million when we're talking about how much, let's say, a soil sample was actually contaminated, or let's say that there is something going on, like your EPA, your Environmental Protection Agency, uses parts per million when they're going out collecting soil samples and they're looking at the soil to determine how toxic it may be, or if it's okay, how much lead levels that there are. You'll see parts per million. Parts per billion is used for very low levels of concentrations, often used in cases where the presence of a substance must be measured with extreme sensitivity, such as public health, environmental science, and toxicology. And then there's that last one, parts per thousand. That's used for higher concentrations, generally in the context of oceanography or certain biological measurements. Now, here's another example of what you need to know for the TEAS exam as it relates to calculations that deals with concentrations of solutions. Concentration refers to the amount of a solute present in each quantity of solvent or solution. It is a measure of how much of a given substance is mixed with another substance. So you can express concentration in many different ways: molarity, molality, percent composition, parts per million, parts per billion, just to name a few examples. Some common units of concentrations are molarity, mass percent, and volume percent. And we're going to actually get into those calculations again in part 2 of our video. Dilution. Dilution is another example of concentration calculations. And dilution is the process of reducing the concentration of a solute in a solution, usually by adding more solvent. Now, the key aspect of dilution is that the amount of the solute remains constant, only the total volume of the solution changes. So how can we think about this? Think about a can of orange juice, okay? So if you're making orange juice from a can, you go to the frozen section of your grocery store and you have a can. So you take that one can of orange juice concentrate, pour it in, doop, 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 and then you add 3 cans of water. You now have 4 cans of orange juice, okay? So that's one way to think about dilution, something that's diluted. Now, you have 2 types of formulas that you need to know. Grams of moles of solute equals grams or moles of solute, meaning that the concentrated solution is equal to the diluted solution. The formula that you will see in part 2, C1 times V1 equals C2 times V2. Now you do need to know what each of those numbers mean and each of those letters. So as an example, C1 is equal to the initial concentration of the solution. V1 is equal to the initial volume of the solution, whereas C2 is equal to the final concentration of the dilution, and volume 2, or V2 rather, is equal to the final volume of that dilution. Note, if C1 increases, then V1 will decrease. Same thing for C2. If C2 decreases, then guess what? V2 is going to increase. So this means that they are inversely proportional to one another, meaning that as one increases, the other one will decrease. Now, you're probably wondering, when will you ever see real-life applications of concentrations and dilutions, particularly in the healthcare field? Well, let me give you 3 classic examples. Medicine. Dilution is used to adjust drug dosages or prepare IV solutions at the required concentrations. Laboratories. Scientists regularly perform dilutions to prepare solutions of desired concentrations for experiments. And then everyday life, when you're preparing beverages like juice from concentrated concentrations, it involves dilution where water is added to a concentrated form of the drink. So for that last example, let me give you a key one. Have you ever had somebody's syrupy tasting Kool-Aid, or let's say a drink or whatever, and it's too sweet to your liking? Well, when you add water to it, that's another form of diluting your solution. Okay? There is one example that you have to know about when it comes to calculations for with dilutions. If you have a serial dilution, it is basically a stepwise dilution process where a solution is diluted multiple times in a sequence. So you have each solution, or dilution rather, reducing the concentration of the original solution by a consistent factor, making it easier to reach very low concentrations. So in a serial dilution, if you perform a series of, let's say, a 1 to 10 dilutions, the dilution factor increases exponentially with each step. So an example of this is like this little image that you see here. In microbiology, you have serial dilutions, which are essential for counting cells or colonies and estimating the number of organisms in a sample. Now, you heard me say dilution factor. So a dilution factor, again, is a ratio that describes how much a solution has been diluted. It is used to determine the concentration of a solute after a dilution process. So the dilution factor quantifies the reduction in concentration that occurs when a solution is diluted by adding more solvent. So you choose a dilution factor, which is the ratio by which the solution will be diluted at each step. So if you want to do a common dilution factor of, let's say, 1 to 10 or 1 to 100 or 1 to 2, this is how you would do it. So you have your solute versus your solvent. So if I have a 1 to 100 ratio, that means I'm going to have, let's say, let's take like 1 liter. That means I'm going to have 1 liter of salt to 100 times that amount, okay? 100 liters of water, just as an example. Now, you probably asked yourself, well, when is the dilution factor even used? In the pharmaceutical industry. So you have dilution factors that are critical in this area because the correct dosage of active ingredients in medications is crucial. Y'all know, like for instance, if a child needs, let's say, 10 milligrams of amoxicillin, and the pharmacist only put 1 milligram because they miscalculated, that child's injury or whatever they're trying to take amoxicillin for, that infection will come right back or not even leave. Like it'll stay long term. And then you're wondering, why is this medication not working? It's because of situations like this, the dilution factor. So again, to highlight some of these formulas that you need to know for solution calculations, they're going to be shown in this next slide. Now, keep in mind, I'm going to give you examples on part 2. so that you can use the mathematical equations that you need to know. Now, they're not going to provide you with these formulas, but I recommend that you do what? I say this all the time, make note cards of these formulas so that you can remember how to calculate them, because you will see them on your TEAS exam. How to calculate various types of formulas, whether it's molarity, molality, parts per million, parts per thousand, dilution factors, and so forth. So here's a classic formula that you will need to know for the TEAS exam, and that deals with molarity. Molarity is defined as the moles of the solute divided by the liters of the solution. So I'm going to give you an example. If you have a 1 molarity solution of sodium chloride, that means it contains 1 mole of sodium chloride dissolved in 1 liter of water. Mass percent is another wonderful example that you will have to know how to calculate. So when you have mass percent or percent by mass, that just simply means the mass of the solute divided by the total mass of the solution multiplied by 100%. Again, I will delve a little deeper in terms of how to calculate this type of problem. Make sure you put them again on your note cards to help you remember these formulas. And finally, our last formula in this series deals with volume percent, percent by volume, which is defined as the volume of the solute divided by the total volume of the solution multiplied by 100%. So stay tuned as we go through these examples in part 2 of the TEAS exam practice on solutions. So, in summary, in part 1 of this video, we talked about definitions and keywords that you needed to know for the TEAS exam as it relates to solutions. In part 2, that's coming up, you must know how to apply those keywords such as molarity, molality, parts per million, parts per thousand, parts per billion, and percent by mass calculations. You need to know how to do those problems. Gather you some index cards, markers, your calculator, your pen, and your paper so that you can remember how to do these problems. If you have questions about anything, please don't hesitate to reach out to us. We'll be more than happy to address your concerns. Take care and good luck on your TEAS exam.